So in this question, we're being asked to find the volume of a largest box that can be created with certain constraints. The first is that 3 of the faces have to lie on the coordinate plane. So my picture here with the boxes, we've got one face back here that's in the YZ plane, we have another that's in the XZ plane, and then one right here in the XY. This vertex here is determined by the equation of the plane that's given in the problem. That ends up being our constraint equation. And as you change the location of where this blue vertex is, right here, say you drag it to the right to a different point that's on this plane, then that'll obviously change the dimensions of your box and then consequently change the volume. So we're trying to figure out where is the optimal place to put this point on the equation of the plane so that volume is maximal. So the volume of the largest rectangular box is telling us that we want to maximize volume. So the function that we are looking to optimize is a volume, but that's the function f that we see in the formula for the setup of Lagrange, of the Lagrange multipliers method. And so the equation for it is just length times width times height of the box, which is x, y, and z, determined by whatever that coordinate is lying in our plane. And then we have our constraining equation. G of x, y, z is going to be equal to x plus 2y plus 3z. So our system of equations is going to come from figuring out where the gradient of f is equal to lambda times the gradient of g, and then we'll also throw in the constraining equation. So what I'm going to do first is find the gradient of f and the gradient of g so that I can see how this gradient equation will distribute into 3 different equations that will go in my system. So the gradient of f, I am taking the derivative of the function x, y, z with respect to each of the variables. So that derivative of f with respect to x should be yz. The partial with respect to y should be xz, and the partial with respect to z should be xy. And then that is supposed to be equal to lambda times the gradient of g, which, taking the derivative of g with respect to x, y, and z will just give you the vector 1, 2, 3, picking off the coefficients of x, y, and z in the function g. Okay, so now when I go to write my system of equations, I'm going to use this vector equation that I just generated right here in order to get 3 different equations using corresponding components. So I know that using the x coordinate, yz should be equal to lambda times 1. Using the y coordinate, xz should be equal to 2 times lambda. And then the z coordinate gives us the equation xy equals 3 lambda. We add to that list, remember, we always put the constraining equation on it, and that's the equation of the plane here, because it's determining what x, y, and z are allowed to be, which then impacts the volume of the box. So there's my system. For ease of reference, I'm going to give these equations each a number so I can refer to them. Now you can do anything you want to solve this system of equations, and you just try stuff, and your goal is to solve for x, y, and z. Lambda, the value of it can change as long as x, y, z is a solution for some lambda. So I end up I'm just going to go ahead and take equation 1. I'm going to sub 1 into 2. So xz equals 2 times yz, substituting for lambda. Now, something to keep in mind here is that there are some hidden implicit constraints in our equation. We are talking about a box, and in order for this to truly be a box, we can't have any of its dimensions equal to 0. So all of x, y, and z have to be greater than 0. The reason I bring this up is because we are now in a situation where we have an equation where there's a z on both sides of the equation, and you might wonder, can I just divide by z? Well, the answer is yes. You can cancel these z's because we know that z is never 0. Otherwise, we wouldn't have a box. So this equation really does simplify to just x equals 2y. So that's what equation subbing equation 1 into number 2 would give us, but we could also sub 1 into 3 as well. And that would tell us that xy is equal to 3 times lambda, and lambda, according to equation 1, is yz. Then we're in this situation again where we have a y on both sides, but we can cancel it because y is always greater than 0, and so we get this equation x equals 3z. So again, what we used here is that z is not 0, which allowed us to cancel for that other equation, and we also use y not 0. So in order for 1, 2, and 3 to hold, we now see that there are 2 constraints relating what x has to be. And notice that this gives me a way that I might take my fourth equation, the equation of the plane, and make a substitution to hopefully reduce this to a single variable equation. So I'm going to go ahead and write my updated system of equations real quick. Our solution process has led to us saying that we have x equals 2y, we've got x equals 3z, and we have x plus 2y plus 3z equals 6. Notice that I could use x equals 2y to rewrite y in terms of x. And I could do the same thing with my second equation, x equals 3z. I could write z in terms of x. And then that will allow me to write my equation in terms of x only, my equation of the plane. So I'm going to get x plus 2 times y, which is x over 2, plus 3 times x over 3 is equal to 6. And then simplifying, I get, this is just an x, this is just an x as well because of the multiplication by the constant. And so from there, this tells me that 3x is equal to 6, which implies that x is 2. And then that means that y and z have to follow their relationship equations that we got with x. And so therefore I can say that my point will be 2, 1, 2/3. So we only got 1 point. Let me emphasize that. We found exactly 1 point. So remember, we're trying to maximize volume, and so we're trying to find an absolute maximum. If there's only one point, that tells me that I only have one extreme value, and we might feel bothered by that. So the question is, though, of the one point that I've got, why must this point be the location of an absolute max? Well, it begs the question, can we have an absolute minimum in this type of situation? Remember, we're finding the volume of a box. Let's ask ourselves, can we minimize it? Well, we know that the dimensions x, y, and z of that box always have to be positive. So that means that I'm never allowed for any of those to be zero. Volume would obviously be minimal if one of the dimensions was zero, but I always have numbers that are positive for x, y, and z, which tells me that I can never find a smallest volume, because I can always shrink x, y, and z a little bit smaller, and have them still be positive numbers, and I'll find a smaller volume. So we want to say that, so this is actually okay. We're not expecting in this physical problem to have an absolute min. There's no absolute min. And the reason why is because having x, y, and z greater than 0 implies that the volume always has to be greater than 0. If I was going to have a minimum volume, it would have to be 0, but it's not allowed to be 0, so I never actually achieve it. So then I just have one point to evaluate in the Lagrange multipliers method, so I plug that into the function f, which is my volume, remember, and that's going to be the value of the maximum volume of the box. And so they are asking us to find the volume of this largest rectangular box, so this is exactly going to be our answer. Remember, our function f was x times y times z for volume, so this is 2 times 1 times 2/3, and that gives me 4/3, and then this is units cubed. So if you wanted to write this out in words, you could then say, therefore, the largest box has volume 4/3 cubic units. And that's it.